Hi all, this is Mr. Yeager with chemistry. Moving on to one of our last units, thermochemistry, looking at how basically heat moves around in reactions. So this is kind of a bit longer part of the video. We're going to look a lot about what is heat, how does it move. We're going to look at trying to calculate heat as well, and why certain compounds or materials absorb heat a little faster or slower than others. What makes those a little bit different, okay? So this is all under the title of thermochemistry, all right? Obviously it is getting warmer, being out in the spring. Hopefully it stays warmer. It's been a little manic. But with this one, we are going to be looking again at analyzing heat transfer, and specific heat. In a couple other videos during this unit, we're going to look at Hess's law, which gets into very specifically the heat of reactions, basically how much heat is released or used during a chemical reaction. We're going to look at kinetics a little bit, and then some phase diagrams and heating and cooling curves. If you're in my class, virtual week, you guys will be looking at some gas laws and everything. But that'll be it, and we'll hit to our last, this is basically our last assessed unit. Okay? So, jumping into heat and heat transfer. First off, let's talk about energy again. We've said chemistry is all based on energy, okay? The idea that every chemical does what it does in order to try to get to the lowest energy level possible. That goes all the way back to basically talking about electrons and why they are set up the way they do. So, energy itself is the ability to do work. That is our technical definition. That itself, as I always say in physics, which we cover energy quite a bit, it's the ability to do something. It's the ability to do stuff, okay? Without energy, you're not doing anything, okay? There's no ability to even start moving, okay? Since we're talking about thermochemistry, we're looking at the energy in the form of heat, or sometimes we call it thermal energy. So you'll see it mixed up. We might just say heat, we might say thermal energy that's produced. We even will use the word enthalpy, all right, to talk about the heat energy in reactions. So, a little bit about energy. There's basically two general types of energy. Again, we get more specific than this in certain classes, but for this unit, for this class, we're going to be primarily looking at kinetic and potential energy. Okay, and kinetic energy is the energy of motion, particles moving around. There is a way to measure that using temperature. We're going to see that in a moment. Potential energy is that stored energy. Now, potential energy comes in many different forms. Basically, again, the word potential is it has something there that could eventually then be used in some other form, like kinetic. Okay, but potential energy primarily comes from the object's position, where we might talk about gravitational potential energy or elastic potential energy. Again, those are more physics-oriented potential energies. Or composition. And composition is the one we're looking at more because we're going to be looking at chemical potential energy. Okay, the energy stored in the bonds, not only in breaking the bonds, but also forming the bonds. Sometimes the atoms will release energy because they become more stable after the bond, okay? Or you might need to put energy into it to force those atoms to come together, but once they're forced together, they will stick together for that time being, okay? So forming bonds requires energy to be pulled in. Breaking bonds releases energy out to the surroundings. Again, the idea that where is that energy going? Are we going to feel that energy, or is that energy being pulled away from us so we actually feel cold, okay? So that is where all of this energy is essentially going, is in between the bonds. And we can even, we're going to be talking about not just chemical bonds, but the intermolecular bonds too, intermolecular forces, okay? So heat itself, which has the symbol Q, is the energy that flows from warm to cold. Heat always moves hot to cold, hot to cold. There's no way heat ever travels cold to hot. Again, we might feel that. We might be like, ooh, feel that warm air coming to me. You know, I'm in the cold, or the cold air rushing to me, all right? But it's always hot to cold. It actually is the idea that you're releasing that energy out to everything, okay? So, you know, here's some just pictures showing that. The heat will travel from the fire hand to the ice hand. Okay, it won't travel from hot to cold to hot. When the dog jumps in the pool, okay, the dog might feel cold if the pool is cooler. The reason it will be cooler, or the dog will feel cool, is as it says, the heat will travel from the dog into the pool water, all right? If the pool is cooler than you, that's why you feel cold. Heat traveling from the air into the dried ice. So this is actually where we're having sublimation occur. So heat is going into, it's going toward the compound, toward the dried ice in order to try to break up some of those intermolecular forces to change it into a gas. All right? And then heat travels from fire to ice, even though it might look like the ice is causing the fire. I don't think it actually does look like that, but whatever. Okay? So again, heat will always travel hot to cold, and heat will travel until both objects are the same temperature. Okay? Until they are the same temperature. So we might see this doesn't mean that they both change the same temperature. They both will reach the same temperature. One might only decrease by 5 degrees while the other one warms up by 15, but they will both match at the same temperature eventually. All right? So let's talk about temperature. Okay, how do we measure temperature? Temperature is measured in degrees Celsius or Kelvin. All right. Again, I couldn't write it with the Google sites, degrees Celsius. So degrees Celsius obviously is degrees C, and Kelvin K. These are our two main scientific units. We do not use Fahrenheit. Okay, I'm not even showing the conversion from Fahrenheit. We don't need it. So, what is temperature actually measuring? It's measuring the average kinetic energy of the particles. How much approximate energy is in all of the particles together. Obviously, one particle might have a little bit more energy than another one. That's why we look at the average kinetic energy. So the faster the particles move, the higher the temperature is. The higher the temperature is, the faster the particles are moving around you, which is why then they collide with you, they transfer some of their energy, and you start feeling hot. Okay? So, we do need to be prepared to convert between Kelvin and degrees Celsius, because while a lot of problems will start you out in degrees Celsius, we need Kelvin for the formulas. Okay? So we have a straightforward formula here. Kelvin equals 273 plus degrees Celsius. Kelvin equals 273 plus degrees Celsius. All right? So it's a pretty straightforward formula. You can see the examples down below. If I say, hey, convert 100 Kelvin to degrees Celsius, well, I'd set it up like this. 100 equals 273 plus degrees Celsius. I simply subtract the 273 over to the other side, and I have negative 173 degrees Celsius. Okay? I'll give you a heads up. 273 Kelvin equals 0 degrees Celsius. So the freezing point, melting point of water is 273 Kelvin. Again, the Kelvin scale was made never to be negative, because we want at 0 Kelvin, that means this is representing what's called absolute zero, and this is where all particle motion stops moving. Absolute zero. Okay? So that's what we're looking at there. So that's why you'll never see a negative Kelvin. If you're getting negative Kelvins, you already did it wrong. So we can have negative degrees Celsius, but you saw how I did that. Here's another example. If I want to change from 45 degrees Celsius to Kelvin, I just do 273 plus 45. All right? Nothing special about that formula. You're either adding it or subtracting it. If we're going from degrees Celsius to Kelvin, I add. If I go from Kelvin to degrees Celsius, I am subtracting. Okay? So, how do I now measure heat? How do I actually put this together? Okay? I measure heat in a couple of different units. The primary unit, as you can see, is this unit, the joule. Okay, the joule. This is the main unit for energy. This is the one we would obviously use all the time in physics class. Sorry, I keep talking about physics because I teach physics so much. All right, joule is our primary unit for energy. But in chemistry, we do like to talk about these two other units, which basically are named the same. We have what's called the calorie and then the nutritional calorie. You can see by the abbreviation, lowercase CAL is what's called scientific calorie. And then when we have a capital C followed by AL, that's the nutritional calorie. The calorie, starting with the one in the middle here, is just sometimes used in place of the joule in chemistry. And what a calorie is it's specifically meaning the amount of energy needed to raise 1 gram of H2O 1 degree Celsius. Okay, 1 gram of H2O, 1 degree Celsius. All right, and that turns out that 1 joule is 4.184 calories. All right, 4.184 calories. It's based on what we're going to see in a moment called the heat capacity or specific heat. But that is the calorie. And again, you can see it's very specifically related with water. It's very much specifically related with water. Now, this is then broken into what's called the nutritional calorie. And basically, 1 nutritional calorie is equal to 1,000 scientific calories, or little calories. All right? We use those on food. That's why we say nutritional calories. So when you read the calorie label, it's giving you the nutritional calories. You actually have to multiply that by 1,000 to get the scientific calories. All right? And then obviously convert that if you want to figure out the joules. Essentially, the idea with a nutritional calorie is it's telling you how much energy is needed to increase the temperature of water inside your body, essentially. All right? But it is a measurement of the energy you would get. Again, that is energy that would be produced and used for different things in your body. Okay? So if you do have to convert, I will give you those conversions as needed. Again, joule and calorie, the little calorie are the more often used ones. Nutritional calorie, I kind of use that in a lab activity that we do. All right, that leads us to heat capacity or specific heat, which is the symbol and formulas for it is C, okay, little c. So heat is Q, heat capacity is C. So this is going to explain that question of how do I know how quickly or slowly something will heat up? It's based on the object's heat capacity. When you get into a car on a very hot day, the seatbelt metal is always the most hot thing in the car. All right? Everything in the car has been receiving the same amount of energy, but the metals in the car are always so much hotter than the fabric, the seat's fabric, maybe even just the material used on the steering wheel or any of the plastics and things like that. The metals are always the hottest. So why is that? And it is based on the heat capacity of those different substances in your car. So the heat capacity, or specific heat, is the measurement of the amount of energy needed to raise a mass. You will see either 1 gram or 1 kilogram of mass, 1 degree Celsius or Kelvin. All right? So that right there, if you read that, you might be going, wait a minute, we just did that. That's the calorie. This is where they are definitely related in some ways with it, okay? Except the calorie is specifically related with water. This is now referring to anything heating up. And again, the mass may be grams or kilograms. The temperature change can be Celsius or Kelvin. Like we just saw with the formula for Celsius and Kelvin, 1 degree Celsius is 1 change in Kelvin. So they are equivalent in that case. But what can we do with these heat capacities? Why does the metal heat up faster than the plastics or the fabric? The larger the heat capacity, the slower the object will heat up. The larger the heat capacity, the slower the object will heat up. Okay? What that is saying is you need more energy to raise the object 1 degree if it has a large heat capacity, which I just noticed I spelled it capacity. Okay? I'll have to go back and correct that. So the larger the heat capacity, the slower the object heats up. Again, what we're saying is everything in the car got the same amount of energy. But because the fabric, if you have like fabric seats, they have very high heat capacities, meaning you need to put a lot of energy into that fabric to raise it 1 degree. A lot. Insulators have high heat capacity. So plastics, water, 4.184 is actually a very high heat capacity. Water is an amazing insulator. That's why we use it in nuclear power plants to slow down nuclear reactions. It absorbs so much of the heat and the other particles. All right? Fabric, like I said, wood, these are all insulators. It'll take a very long time for them to heat up because they need to absorb a lot of heat to go up just 1 degree. The opposite is then true. The smaller the heat capacity, the faster the object heats up. Less energy needed to raise it 1 degree. Conductors, like metals, have low heat capacities. All right? So to kind of give you an idea of this, all right, let's say I have a metal. Most metals have very small heat capacities. I'm talking about like 0.25 joules over grams times degrees Celsius. What this right here is the heat capacity. You can see the units are joules over grams times degrees Celsius. So what I'm saying is for every 0.25 joules of energy that goes into the metal, it'll increase the metal 1 degree Celsius. Okay? Now let's put on the other side, let's like say we have fabric. For the fabric, I'm saying it needs, I'm going to keep the number small just so we can see the difference, 2 joules per gram times degrees Celsius. So it needs 2 joules to go up 1 degree. So let's say, for example, these two things are in the car. Excuse me. And the sun is shining. And it's sending 2 joules of heat into the fabric, and it sends 2 joules of heat into the metal. Those 2 joules of heat in the fabric will increase the fabric 1 degree Celsius. But the 2 joules of heat into the metal, which for every 0.25 joules of heat, it goes up 1 degree. So if I do 2 divided by 0.25, it will go up 8 degrees Celsius. They're both receiving the same amount of heat. It's just because the metal has a smaller heat capacity, it will increase in temperature more quickly than the fabric will. Okay? So that's where, again, we want to make sure it's clear. Both of them are receiving the same amount of energy, but one will heat up faster than the other. All right. So that finally leads us to my heat capacity formula. Heat is equal to mass times heat capacity times the change in temperature. All right. This is often written as Q equals M times C times delta T. Okay, M times C times delta T. All right. Delta T, change in temperature, is where you have to subtract the final temperature minus the initial temperature. That's your change in temperature. This can be a positive number. This can be a negative number. So we can have a positive or negative Q. A positive Q means you are absorbing energy. Okay? If you have a negative Q, you are releasing energy. Okay? You are releasing the energy. So that is going to be important as well to try to notice. That's something that's going to be consistent through all of this unit. So positive means you're taking the energy in. Negative means you're releasing the energy. All right? So we're going to have to use this formula, okay? I'm going to come back to that in a moment to show you some examples, okay? One last thing. How do we actually do this in the lab? How do we actually measure heat coming from a particular substance? We're going to do this in the lab where we're going to try to measure the heat being produced by a potato chip, okay? But if we want to do it really, really right, we use a device called a calorimeter, which is what's shown on the left there, okay? A calorimeter is basically an insulated container. It's what like thermoses basically are. Okay, a lot of the thermoses are really good about it too. It's an insulated container. What that means is no energy should get out and no energy should come in. And so what we can do is we can set up a chemical reaction inside this container. And again, it's just we still try to have a little bit of air come in, so if it's trying to burn, we can let it do that. And I can measure the change in temperature that occurs. So I know the mass of the object, I hopefully know the identity of the object, so I can look up the specific heat. The specific heat, I guess I didn't mention it, is a constant for a particular substance. So if I have iron, iron has a particular specific heat. Water has a particular specific heat or heat capacity, okay? But I could sit there and go, you know, hey, let's put this object into the container. Let's heat it up for a little bit. I can measure the change in temperature that occurs. And if no energy is being released or absorbed, we know everything's coming from that chemical reaction that takes place. So that is in something called a calorimeter. Okay? So let's practice a couple of problems. So again, my formula is, I'm going to write it once onto the other side, and then we'll just keep doing it. M times C times delta T. All right? You do have to pay attention to the units some. You will see that I sometimes use joules, kilojoules, grams, kilograms, so just pay attention. But let's just do a few of these so you can see how this works. So how much energy is needed to raise the temperature of 55 grams of aluminum from 22.4 to 94.6 degrees Celsius? The specific heat of aluminum is 0.902. So what I would do here is this would be Q equals mass is 55 times specific heat is 902. I can put grams, joules, grams, Kelvin. Okay. And then times the change in temperature. Now I know it says in Kelvin there. We should technically change it over to Kelvin. I'm going to go ahead and do that just so we get some practice. So 273 plus 22.4 sorry, let me do something here. There we go. Is 295.4 Kelvin, and then Kelvin equals 273 plus 94.6 is 367.6 Kelvin. Well, the thing is, I technically don't have to do that because I'm just going to subtract them anyway. And again, they're 1-to-1 ratios, equivalent values. 1 degree Celsius is 1 Kelvin. So I could have just subtracted them, but I'm going to, again, do this all nicely and correctly. I subtract those two, 367.6 minus 295.4. This comes out to 72.2. And then I multiply everything out. 72.2 times 0.902 times 55. My energy released is, or absorbed, sorry, 3,000. I need to go down to only 2 sig figs. 3,600 joules is my answer. All right. So again, not to get you too confused, I did convert my temperatures to Kelvin. I then subtract them. This is the change in temperature. And then I multiplied it by the mass and the specific heat. So be prepared. You will get some very large answers on this because you're multiplying 3 numbers together. Okay? All right, let's try another one. A 4-gram sample of glass was heated from 274 to 314 and was found to have absorbed 32 joules of heat. What is the specific heat of this type of glass? So in this one, it would be, I have the joules, 32 joules equals 4 times specific heat, I don't know, times 314 minus 274. That would be 40. So times C times 4 equals 32. So I would do 32 divided by 4 times 40. And I get essentially 0.2. Okay? 0.20 joules over grams times Kelvin. That would be my units. How much energy will the same glass sample gain when it is heated 314 to 344? I'll do this one and maybe one more. It would be Q equals 4 times 0.2 now times 344 minus 314, 30. So 30 times 0.2 times 4 equals 24 joules. Sorry. And there's your answers. Okay? So hopefully a pretty straightforward type formula. Just it shows good algebra with it. Let me go down and check out like number 4. Number 4 might be one that's maybe quote unquote a little bit more tricky. Okay. You have 980 kilojoules of energy added to 6.2 liters of water at 291 Kelvin. What will the final temperature be? Okay. So I'll go ahead and help you with this one because this one's pretty tough. Okay. So a couple things. Okay. If I do this, I'm trying to think, sorry, already right now. This one is definitely tougher. I'm going to start with the 6.2 liters of water. That's not mass, but it turns out 1 liter equals 1 kilogram of water. Okay, that is the density. We already know 1 milliliter is equal to 1 gram, so if I increase both by 1,000, they go together. So this is 6.2 kilograms. Okay? All right. This is also talking about water. One of the specific heats we should get used to is we're going to use 4.184 joules per gram times Kelvin a lot. We're going to be using this quite a bit. All right. Since I am in kilograms and in kilojoules, I essentially, actually I think this comes out to the same number because I would what? Divide and then multiply. This is actually also equal to kilojoules, kilograms times Kelvin. Okay. So again, you might have to play around with your units a little bit, not trying to really confuse you, but the idea would be, I mean, I'll show this, 4.184 joules over 1 gram times Kelvin. I would technically have to do 1 kilojoule divided by 1,000 joules, but then I would be doing 1,000 grams over 1 kilogram, and then my units would all match up nicely. Okay, so the 1,000s also cancel out. So my specific heat is still 4.184. So I would do 980 equals 6.2 times 4.184 times delta T. I'm going to solve for the change in temperature. So 980 divided by 6.2 divided by 4.184. I get a change in temperature of 37.77 degrees Celsius, 78 degrees Celsius. That means the temperature went up 37.789 degrees Celsius, sorry, Kelvin. So I'm just going to add that to 291. Technically, this would be 37.78 equals final temperature minus 291. Add 291. And then do sig figs, which is only 2. My answer is basically 330 Kelvin. 330 Kelvin. Okay? Is what I'm looking at there. Or 329 if you want to round it. Well, it should be 330. All right? So use the formula well. Watch out of units. You do have to pay attention to those. Pretty straightforward though. Just plug everything in as you need and solve appropriately. And we can go from there. And again, heat always goes hot to cold. Low specific heat means it will heat up fast or slow. High specific heat heats up slowly. Okay. Thank you very much.